Hello, in this video I'm going to take a look at binary stars. This is where we've got two stars that are orbiting each other. They're gravitationally bound, they've been formed together, and then they orbit around a centre of mass for that system, so a common centre of mass. You can see here in this picture on the left that the stars don't have to be very similar to each other. In this picture, the main star in the middle, the bright one, that's Alpha Centauri. And then down here at about 8 o'clock, we got a small little dot. This is Proxima Centauri, much smaller, much dimmer, and these are orbiting each other though. Takes them a long time to orbit, but they are gravitationally bound. So binary stars are quite popular with amateur astronomers, particularly in urban locations, because they're not as affected when you're observing them by light pollution. So deep sky objects, the really pretty stuff like galaxies and nebulae and planetary nebulae and such like, tend to get swamped by light pollution. So binary stars, although it's nice to have a really dark sky, it's always a benefit when you're observing, pretty much anything. It doesn't matter as much. You can still get a fairly modest telescope and then start splitting these systems and see if you can actually make out the two separate stars. Some stars are separated with the naked eye, but not many. Mostly you're going to require some kind of equipment. But let's go back historically before we get into how we actually separate these stars. And let's go back historically to when they were discovered, because we're coming back again to the problem of distance. If you were looking at something like this through an eyepiece and you were seeing these two dots here, we've got the same old problem. How do we know whether they are close, as in they are actually at the same distance, more or less, or whether Proxima Centauri is actually just much, much further away and they just seem to be close? Now, how do we know how far away the stars are? Because if we don't know they're the same distance, we can't say that they're binary stars. So we need more evidence. We need some kind of backup for this, knowing they exist. So we're going back here to the 18th century, middle of the 18th century. This chap called John Mitchell. Okay, he didn't have a T in his name, but he was an English astronomer, philosopher, mathematician. And he did a statistical analysis, which was unusual at the time for the first evidence to be statistical when it came to astronomy, at least. And he did a statistical analysis of the distribution of stars in the sky. And he was concluding that this was not a random distribution. There were too many stars that were in pairs and groups. For example, we looked at the Pleiades, the star cluster in Taurus, and he calculated that that's about 1 in 500,000 chance to get that number of stars in such a small area of the sky. 1 in 500,000. Okay, you might get something like that, but then there's all these other star clusters that are kicking around and all these other stars that are in very close proximity. So his conclusion is that a lot of these systems are actually gravitationally bound. These are clusters of stars, these are pairs of stars, and it's not a completely random distribution across the sky. Of course, subsequently, now we think it's about a third of the galaxy. A third of the stars in the galaxy are binary systems. So there's loads of them. These are not uncommon objects. It's not like globular clusters or other objects where there aren't that many. We're counting them in 100, 200 of them, something like that. Here, we've actually observed well over 100,000 of them, and there's been billions of the things in our galaxy, and then there's all the other galaxies, so loads of them around. After Mitchell, though, it was then William Herschel, surprise, surprise, he started studying these binary systems because they were also parallax candidates. So sticking with our distance measurements, remember what we were saying with distance measurement, you've got parallax. If you've got a nearby star, then its position relative to background stars will change throughout the year, depending on where the Earth is in its orbit around the sun. So if that's the sun, you've got the Earth at two extremes, diametrically opposite. Then looking at the star from one side, we'll put it over here. Looking at it from the other side of Earth's orbit, we'll put it over here. So we've got this relative motion of this star relative to the background stars that are much further away. So Herschel was looking at these binary stars because they can exhibit similar behavior. If you've got two stars that are orbiting each other, then you'll get a similar effect. because they're moving around and around each other, you've got an extra component to their motion. So relative again to the background stars, it looks as though they've moved. So how do you know whether you've got a nearby star exhibiting parallax, or you've got some system, some binary system, which is exhibiting motion, orbiting these two stars, orbiting each other? So Herschel was observing loads of these. He took observations over 20 or 30 years and such like. And he concluded that a lot of these systems were binary systems that were orbiting each other rather than exhibiting parallax changes. So this is how they were starting to get catalogued. So Mitchell first of all established the almost certainty, the statistical certainty of their existence, and then people like Herschel started classifying them and cataloguing them through these detailed observations. Now there are a number of ways of splitting binary stars. We've got visually, just looking at them, with your eye through the eyepiece, so you can see these stars are close together. That certainly covers a lot of the bright stars. Some of them you can just see with a naked eye. You've got Mizar in Ursa Major, which you can look at. You can, just looking at it on a still night, you can see that it's two separate stars. I'd recommend giving it a go if you're in the northern hemisphere. If you've got a still night, a clear night, and you've got reasonable eyesight, then you should be able to see that is two separate stars. You'll have a lot of them that modest telescopes can easily visually split that they are two separate stars. But again, you're going to want a bit more proof. Okay, that might push you into thinking, well, this is a good candidate for a binary system, but how are we going to guarantee that they are actually bound together? This is where you want to move into getting more evidence, such as spectroscopic evidence. So you can look at the stellar spectra of the star, of this pair of stars that you're looking at here. So if we were observing Alpha Centauri, Proxima Centauri, let's take spectra of these stars and then see if we got Doppler shifts. Because if they are orbiting each other and the orientation of the orbit is such that they've got components of motion towards or away from the Earth, then we're going to see red shifts and blue shifts in their spectra. So we're going to get those Doppler shifts. And as I say, this depends upon orientation. If we've got the orbital plane and we're looking at it perpendicularly, so we've got stars going round in these near circles orbiting around each other, but we're just looking straight down onto that plane, well, we're not going to get any motion away or towards our observation. If the stars need to be moving towards or away from the Earth, so we don't want to be looking at the orbital plane in a perpendicular direction. We want to be, well, ideally parallel would be great. So if we've got our plane with a star on either side, one star's moving out of the screen, one star's moving into the screen, then we've got maximum Doppler shift. So that's going to be great. Usually you're going to have somewhere in between, aren't you? You're going to have some kind of component. And we can measure those with spectroscopic observations. So that's a good way of getting some evidence to show how those red shifts and blue shifts are coordinated with each other of the two stars that seem to be close in the sky. We've got photometric observations that we can do. So this is looking at brightness. We've got photo there for describing it being a brightness observation. And these are looking at eclipsing binaries. So that almost tells you everything you need to know about those. So we've got one star passing in front of the other, and then we get a change in the brightness of the overall system. Again, it depends upon orientation because we need to have one star eclipsing the other. If it isn't passing in front, we're not going to get the brightness change. And we also want with those relatively frequent and prolonged eclipses. Otherwise, it's not going to be practical for observations. If this is happening every 100 years or every 1,000 years, well, we can't hang on that long in order to wait for the next eclipse. So that's something. And we also want the eclipse to last for a while. So we've got time to gather some good data. Now, the most famous example for that, certainly in the northern hemisphere, is Algol and Perseus. This varies from a plus 2.1 magnitude to plus 3.4 magnitude. So that is a big change in magnitude. So it's got that on its side. It's also got the frequency. This is around about every 3 days that we get an eclipse, and the eclipse lasts for about 10 hours. So Algol ticks all of the boxes when it comes to being for eclipsing binaries. So Algol is great. Again, as I say, it depends upon orientation and all of these other setups of the binary system. So that's our third option. Fourth option, we've got astrometric observations. So this is measuring the path of a star in the sky. Quite often, this will be a way of noticing a binary system where one of the stars is invisible. Quite often we're going to go in, usually we do a visual observation. We see that these two stars are in close proximity and then start gathering more data spectroscopically or photometrically or whatever. If you've got a binary pair where one of the two stars isn't visible, say it's a neutron star, well, you're not going to pick that up looking at it through the eyepiece of a telescope. So you have to pick it up in other ways, and this will be through its motion. If there's a bit of a wobble, so if you see a star which is a bit wobbly in how it moves across the sky, then you might deduce that, well, actually it's moving and it's orbiting at the same time. So we're seeing some kind of relative motion against background stars, but we're seeing it for just one star, not for both of them, because you can't observe the second star visually in that binary pair. So if it's close enough, so we're talking about less than, say, 10 parsecs, if it's close enough, you might be able to accurately measure the position of the star in the sky. And if you see this wobbly movement, then, well, maybe it's orbiting as well as just moving across the sky in the usual fashion. So that's quite a difficult one to do. If the star's too far away, you just can't measure the motion with sufficient accuracy. So it needs to be relatively close. So there's a number of ways of figuring out if something's binary or not. Start with the visual and then move through other ways of then convincing yourself that it is actually a binary system. Some binary systems will pass matter from one to the other star. Some of them might even merge. The most notable ones when it comes to passing matter from one to the other is where you've got a white dwarf being one of the stars, and the white dwarf is taking more and more matter, particularly if you've got, say, a giant star with it. Matter from the giant star starts accreting onto the white dwarf, the much denser star, and the white dwarf gets more and more and more mass until it hits 1.44 solar masses, and then it goes supernova. It's reached this critical mass, and you get a type 1a supernova, which is one of the phenomena that I mentioned in the distance measurement video. Type 1a supernovae are great for working out how far away a particular object is because they're so uniform in their behavior. They all go supernova at the same mass. Orbital periods for binary systems can vary a lot. Some of them are just hours. You've got ones like here that I mentioned, Algol, which is a few days. Some of them take hundreds of years, thousands of years. This pair here, Proxima and Alpha Centauri, they take ages to orbit each other. So some of them take a very long time, some of them don't. There's a lot of variation. And this sort of variation is very useful then, because binary stars aren't just there. It's not just the challenge of, oh, can we tell whether they're binary or not? Okay, that's useful. We want to catalogue everything. But they give us a lot of information about star formation. If you analyse particularly the angular momentum inside these systems, then that certainly helps to build up models about how stars are formed. So that's then going back to our nebulae and how those gas clouds are contracting, how protostars and stellar systems are forming, and angular momentum, because it has to be conserved along with various other things. But angular momentum is conserved in these systems, then that gives us something to track, something to build into the models of how these stars are formed. So it is very useful information for working out things like that, the life cycle of stars. Some systems go way beyond just being binary, so you can get multiple systems. So Castor, for example, a bright star in Gemini, you've got Castor and Pollux, the two bright stars in Gemini, and that is actually 6 stars. You've got 3 double stars all in one system. So it can get quite complicated in the number of stars that are then orbiting around each other. So that'd be quite an interesting one to, if they're building up a model of how these systems form, then that's pretty intricate, getting 6 stars forming and then being all gravitationally bound. So yeah, very complicated systems. The most famous one, I think, for that is the one that actually gets referred to as being the double double, and this is Epsilon Lyrae, a fairly bright star. You can tell this is an epsilon, so you're not that far down the Greek alphabet, and it's in the constellation Lyra, so Epsilon Lyrae, which is the double double, and it's very easy to observe because it's quite bright and the separations are quite nice in the stars. This is, as the name suggests, 2 double stars. So you'll get one of them. If you observe the first double, it might look something like that, quite easy to separate. But then for a much larger separation off to the other double star, then you get another double which is sort of perpendicular. It's rotated 90 degrees from the other binary pair. So you'll see something like that through the eyepiece, and it is pretty easy to pick that one out in, again, Northern Hemisphere star, and a nice one for, well, to begin with, really. I'd say that would be the first 3 you'd probably want to go and observe if you start looking at binary stars, would be Mizar, Algol, and Epsilon Lyrae. So they're certainly the place to start. So there's a lot there in binary stars. It's a challenge just to catalogue them, but they do give a lot of information as well on how stars are formed. So yeah, well worth knowing about and well worth having a look at if you get into a bit of amateur astronomy.